Okay, we have problems 1 through 4, which are basically a matching game. And so we have the original function and the graph of f prime. Kind of done something like this before. So let's just start with this. So this has a constant slope, and it is negative. So we should look for the curve that has a negative value, so the curve of the derivative is going to be a horizontal line, and the y value is going to be -2 because that's the slope, because we go rise is -2, run is 1. So we see right down here at the bottom, D matches up with 1, so we'll put D right there. So this is D. Okay, the next one, the slope is positive and then negative. So it's going, and it approaches infinity, so the function is undefined, therefore the derivative is undefined. So it's positive and then much more positive, then it becomes negative and then less negative. So this one, C, has those characteristics. And that's the only one that has those characteristics. So we can say this is C. Here we have a periodic function, so the derivative of a periodic function has to be a periodic function. And here's the slope is 0. Here the slope is 0. So if we go and look at the periodic function, you'll see that the value is 0, the value is 0, because the slope is 0 on the original curve. So that one's easy. So this is, so the third one is A. And so by process of elimination, we know the last one is B, but let's just look at it. So the slope is positive, 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 goes to 0 here, and then goes to negative infinity. So let's see if that's what happens. Here it is. So the slope is positive. And we're not looking at the slope of this line, we're looking at the value. The value is positive. The slope is positive until here where it's 0. There it is, 0. And then it continues the other direction. It becomes negative, but it becomes negative very quickly. And at 2, it goes to negative infinity. Or it approaches negative infinity. So that obviously is the correct answer. So this is B. Okay, so now we're into these longer problems. We have 4 of them. So what it says is analyze and sketch a graph of the function. Label any intercepts, relative extreme, and points of inflection in asymptotes. Use graphing to verify your results. So we basically fill out the tables like in the book. And those tables include pretty much all intervals that are separated by points of inflection, critical numbers, intercepts. So just thinking here, before we get going, let's make sure I have it all correct. Well, actually, the tables do not include the intercepts. They just include the points of inflection and the critical numbers, possible points of inflection. So our first problem is problem number 12, which is a rational function. So the thing to do is to find the critical numbers and also the points of inflection, or possible points of inflection. So we're going to take the derivative and the second derivative. And we'll use the quotient rule. So let's just call this h of x just to, so I can use the other letters. So we could break this into 2, but in this case I'm going to use the quotient rule. So the derivatives are 1 and 1. So the quotient rule would say h prime of x is equal to these two multiplied together minus those two. So we get 1 times x minus x plus 2 times 1, all divided by x squared. You can see we have 1x minus 1x, so the x parts drop out. We just get negative 2 over x squared. So that's the first derivative. Let's go ahead and take the second derivative while we're doing it. That's actually pretty easy because this is, I can rewrite this as -2 times x to the minus 2 power. So you get that correct now. So the positive exponent in the denominator becomes a negative exponent in the numerator. So then we take the derivative. You take -2 times -2 is positive 4 times x to the minus 3 power, or 4 divided by x cubed. So those are my first and second derivatives. So the critical numbers are going to be where this is undefined or 0. Well, there's no cases where it's 0 because the numerator is always 2. So where it's undefined, we're going to have a critical number at x equals 0. And if you look at the cases where f or h double prime of x is equal to 0 or undefined, h double prime of x is equal to 0 or undefined at x equals 0 as well. As you can see, there's no time the second derivative is 0. So if you divide by 0, you'll get an undefined second derivative, which is 0. So they're the same point. So in this case, it's not really that much more difficult than what we normally do. We're going to have just one critical number, which is one value of x that we'll put in the table. So that means we have, and the way we do this is we do it kind of the other way around. We're going to have, if you look at the book, you have one with the interval, one with the first function, the first derivative, the second derivative, and some comment. So you got 5 of those, and we've got 2 intervals. So that's the size of the table that we need in this case. So again, look at your book, and it says f of x is here, f prime of x is there, f double prime of x is there, and then we have comments, I guess. And in this case, we have the intervals. So the intervals go this direction. So we go from negative infinity to 0, and from 0 to positive infinity. So as far as the value of the function, it's undefined. I'll put UND for undefined. And also, and that's because there's a vertical asymptote. So we have a vertical asymptote at x equals 0. Now, the question is, what is the second derivative? And here, first derivative and second derivative, we don't put in the numbers, we just put in the signs. Oh, I'm sorry. The function is defined. It's 0 that it's not defined. So, but we're not talking about a particular point. And that's actually, I should have one more column, one more row here. That's my fault. So let me undo some of this stuff here. Let's start over again. You actually have to have one additional thing. So we have 5 columns always, and then you have one column for each critical number, and then you have to have 2 rows, 1 row for the critical number and 2 rows for the intervals. So it's a little bit bigger than I originally started out with. Okay, so let's try this again. The value of the function, the value of the first derivative, or actually the sign of the first derivative. The only place we put values is f of x. And I'm not going to put interval because actually they're not all intervals. So in this case, we do have the case where x equals 0. So in contrast to what we've done so far, we actually want to include every point in the domain, not just the intervals that are outside of it. So anyway, at x equals 0, the function is undefined, the first derivative is undefined, and the second derivative is undefined. And that's because it's a vertical asymptote. Now, we don't actually write in the function here. We just we only write the function value in for the critical numbers for the points of inflection and things like that. Here we just put in the sign of the first and second derivatives. So if you look at the first derivative right here, negative 2 over x squared, you can see this is always negative. So we go here and we put in negative, and we put in negative in both of these intervals. And at 0, it's undefined. Then you do the same thing for the second derivative. Well, the second derivative is cubed, so when x is positive, you're going to have a positive divided by a positive number cubed, which is positive. So the second derivative is going to be positive, and the second derivative in this negative interval is going to be negative, because a negative number cubed is negative. So you have positive divided by negative, which is a negative. So what this tells us is that, and I'm going to write this in blue, is we have a decreasing function. We have a decreasing function. Here we have concave down, and here we have concave up. And that's what we would actually put in the comments, but I'm running out of space, so we would put in decreasing down. This is decreasing up. Okay, what else do we need? We need the x-intercept. The x-intercept, you take the original equation and set y equal to 0. So what's our original equation? It was, which one are we on? 12. So y is equal to x plus 2 over x. So the question is, when y equals 0, when the numerator is equal to 0. So we have solve for x, and so that's our x-intercept. We could do that, or we could say it's negative 2 comma 0. The point negative x equals 2, y equals 0. For the y-intercept, we set x equal to 0. So if we do that, we get 0 plus 2 over 0, which is 2 over 0, which is undefined. And that's because we have a vertical asymptote on the y-axis is a vertical asymptote. So then we talk about asymptotes. So we have vertical asymptotes when the denominator is 0. Denominator is 0. So when does that happen? So x equals 0. The denominator equals 0 when x equals 0. So this is a vertical asymptote. And a horizontal asymptote, we take the limit as x approaches infinity of x plus 2 over x. Okay, so these are the highest order terms, x is to the first power, and the leading coefficients are 1, so we just look at the ratio of the leading coefficients, so the answer is 1. So y equals 1 is a horizontal asymptote. Okay, and our domain is all real numbers except x cannot equal 0, because then you have a it's undefined at x equals 0. Okay, given all that, now we can do a graph. So let's put our vertical asymptotes. Those were at 0, so we have a vertical asymptote at 0. We have a horizontal asymptote of 1. Draw these away from the center just so it leaves room to do stuff in there. So those are limits as x goes to infinity. We have an x-intercept of -2. So let's put that on there. -2 right there. There is no y-intercept. And also from our table, if we look at this, we had the domain was broken up into two parts, greater than 0 and less than 0. So what we said here was that it was decreasing and it was concave up, and this was decreasing and it was concave down. Let me see if I remember that correctly. Decreasing, decreasing, down, up. Okay, so let's think about this. If we're approaching this horizontal, this is a vertical asymptote, so we can either be coming from this direction or we can be coming from this direction. Well, if we were coming from this direction, we'd have to cross the x-axis, which we can't do. So that precludes the fact it can't come from down here, so it has to come up from up here. And so it would turn this direction. Notice it's decreasing the entire time, going from positive, less positive, less positive, so that checks. And also it's concave up, so that also agrees. If I'd drawn it this direction, it would be increasing, which would be wrong, and also it would be concave down, which would be wrong. So both of those, there's a couple of things that mean that it's going to be this one. One is because it has to be concave up, it has to be decreasing, also because there's no x-intercept, it can't come from down here, so that works out. Okay, now here we have concave down and it's decreasing. So if we come from this horizontal asymptote here, then we know it keeps decreasing because it then goes down to 0, and it has to keep decreasing like this. Like that. So how about these other things? Is it decreasing? Yes. Is it concave down? Yes. If I'd come from the other direction, if I'd said it was approaching this side and I went this way, for one thing, I wouldn't have an x-intercept. Secondly, is it would be concave up and would be increasing, so it doesn't satisfy any of those. You could say, well, what if it went, you know, could I have it go where it goes like this and then comes down like that and then back up again? Well, the problem with that is you would have concave down here and then you would have concave up here. So you have a change. You have to do that. You'd have to have a change in concavity, which doesn't happen. So it has to be, and it also would change from increasing to decreasing. So all of those factors lead us to the conclusion that that's what the figure looks like. And I closed the graphing program, so I need to open that up again. So let me just plot that and just wait a second until I plot this function. So we actually have more stuff than we needed to know to be able to do this thing. Okay, let me add a page. Slide that over there. So there you go. That's exactly what we have. What do we have? Do we have everything? Let's draw everything we have. We have a horizontal asymptote of 1. We have a vertical asymptote of 0. We have an x-intercept of -2. We're concave down here, we're concave up, and we're decreasing through the entire thing. So except for the scale of the axes, you can see that everything agrees. Okay, next problem is 17. So we have rational function. But one thing is we have, since this is higher, x squared is higher than x to the first power, this is going to have a slant asymptote. And So we'll need to figure out what that slant equation is at some point. But we're going to go ahead and find the first and second derivatives first. So again, I'm going to write out what the numerator and the denominator are and call each one f of x and g of x respectively. So then we take the derivative of the numerator, which is 2x minus 6, and the derivative of the denominator, which is 1. So y prime is going to be 2x minus 6 times x minus 4 minus x squared minus 6x plus 12 times 1, all divided by x minus 4 squared. Okay, so let's go ahead and simplify the numerator. So we'll get 2x squared minus 6x minus 8x plus 24 using FOIL. And then we have the second thing. I'm going to apply this negative sign, so everything gets its sign changed. So this becomes negative, this becomes positive, that becomes negative. And we divide that all by x minus 4 quantity squared. So we have 2x squared minus 1x squared gives us x squared. Negative 6 minus 8 is negative 14, plus 6 is negative 8. And then we have 24 minus 12, which is 24 minus 12 is 12. And that's all divided by x minus 4 squared. So that's the first derivative. And we're going to take the second derivative. So the derivative of the numerator is 2x minus 8. And the derivative of the denominator is going to be 2 times x minus 4 to the first power times the derivative of what's in there, which is 1. So g prime of x is basically 2x. Well, let's keep it as factored because we're going to be able to cancel some of that stuff out. Okay, so now we use the quotient rule. So we take that times that, so we have 2x minus 8 times x minus 4 squared minus x squared minus 8x plus 12 times 2 times x minus 4, all divided by x minus 4 to the fourth power, because we square that. Now you can cancel out an x minus 4, so we'll get 2x minus 8 times x minus 4 to the first power minus x squared minus 8x plus 12 times 1, or times 2, because the other thing cancels out. And in the denominator we have x minus 4 cubed instead of the fourth power. So now we multiply this stuff out again. We'll get 2x squared minus 8x minus 8x plus 32 from FOIL. And then we'll get negative x squared plus 8x minus 12. All divided by x minus 4 cubed. And 2x squared minus x squared is just x squared. We have negative 16 plus 8, which is just negative 8. And then we have 32 minus 12, which is 20. All divided by x minus 4 cubed. So that's the second derivative. So we're going to find the critical numbers And also, so what are the critical numbers? Let's go back to the first derivative expression. So I'm going to slip something in there. So we're looking at two cases where the numerator is 0 and where the numerator is undefined, which is a negative and positive, or a positive 4. So we're going to, let's work this out first. So can we factor this thing? Yes. It's going to be x minus, actually 6 and 2. So we have x minus 6, x minus 2, 0. And so we get a critical number at x equals 2 and a critical number at x equals 6. Also at x equals 4 due to f prime does not exist. So that is, we have at least three numbers. And then if we go to the second derivative here, same kind of deal. This one's going to match up exactly. So the second derivative does not exist. The function does not exist. So then we set this equal to 0. And is there a nice answer? I don't think so. So we're going to have to use completeness square. If we do, it'll still come out this way. So we get negative 20. And so you take negative 8 divided by 2, square that. That gives you positive 16. So add 16, you add 16. And the problem is that the right-hand side is now negative. And if you ever get to this point where it's negative, then you know you're done for. So there's no real solutions to that. No real solutions. Therefore, no possible points of inflection. So if there's no possible points of inflection, then there's no points of inflection. Okay. The reason I said possible, because if you had solutions, then those would be possible points of inflection. In this case, there are none, so there's nothing to try out. So we break this up into intervals. We have 4 intervals and 3 numbers. So let's add a page. We're going to make it a table. It has 5 columns, and we're going to have, then we have 1, 2, 3, 3 numbers, and 1, 2, 3, 4, 4 intervals. Okay, I'm going to put this on one page so that we can see it a lot easier. So we're going to go, let's write the numbers down. 2, 4, and 6. Okay, so those are the numbers. 2, 4, 6. Okay, so from negative infinity to 2, x equals 2. Then you go from 2 to 4, x equals 4. 4 to 6, x equals 6, and 6 to positive infinity. So you can see I've covered the entire domain. And then here we put f of x, here we put f prime of x, here we put f double prime of x, and then our comments. Okay, so let's start with the second derivative first. So what happens is that because there are no real solutions here, this never goes to 0, so it's either always got to be positive or always negative. So we could plug 0 in there. And so if you put 0 in there, you get 20. If you put, let's say, 10 in there, you get 100 minus 80, which is 20, plus 20, which is 40. That's positive. If you put a negative 2, you get negative 4. negative 4 times 8 is positive 32, so you end up with positive anyway. So it's always positive. So we can go over here and say this is positive, 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 positive. We actually put positive all the way through here. So it's going to be concave up for all cases. And I'm just going to check. I'm going to check the answer here just to make sure I'm not messing up so I don't get too far. I don't want to go work this whole problem out. I have to re-record it. So this is problem 17. Well, actually, we do have to worry about it. I knew there was something fishy because it didn't make sense. Okay, so we're going to redo this here. Okay. So one thing I didn't do is really I need to look on either side of negative 4. So even though we don't have any real solutions, we still have this vertical asymptote. So the question is, less than negative 4, it's going to be one value, and greater than 4, it's going to be some other value. So what we found was that for x equal to 0, this ends up being, yeah, there we go. Okay, so I did that wrong. I forgot the denominator in the whole equation. So let's just do it here. I'm going to add a page and rethink this. Okay, so anyway, let's say y double prime of 0. What you get is 0 squared minus 0 plus 20 divided by 0 minus 4 cubed. So we get 20 divided by negative 64, which is negative. So it's negative. And the other case is the other interval would be greater than 4, so let's put it 5. So we have 5 squared minus 8 times 5 plus 20 divided by 5 minus 4 cubed. And so the denominator is positive. 5 minus 4 is 1. So it's actually positive 1. And in the numerator, we have 25. So this is always positive. We determined that earlier, so it's positive. So in this case, it's positive. So from that, we can say that it's concave down up to this point, and then it's concave up after that point. Okay, that's my mistake. Okay, now, as far as this is concerned, we're going to look at the first derivative. And we know the first derivative is 0 here, and we know the first derivative is 0 there, and at 4 it's undefined. Now we just need to figure out what it is at these values. So let's go back to the first derivative, which is that equation. So I'm going to copy that. And again, unfortunately, it doesn't allow me to copy, so I got to drag this thing through a couple of screens. Okay, so there's the first derivative. So what's going to happen? Well, the denominator is squared, so the denominator is always positive. So we'll just put a positive sign down there. Now, then we look at, well, here we could put in 0. So for the first one, this first interval, we could put in 0. And so if we put in 0, you'll get 0 minus 0 plus 12. So you get plus 12, which is positive. So this is going to be positive, which means it's increasing. Okay, then we go to negative 3, or positive 3. So let's see what happens to the numerator in that case. So at x equals 3, we get 3 squared minus 8 times 3 plus 12 all over 3 minus 4 squared. Again, the denominator is always positive because you're squaring it. And here you get 9 plus 12 is 21 minus 24 is a negative number. It's actually negative 3. So when we go up here, this becomes negative. Then we do it x equals 5, which is in the next interval. So we'll have 5 squared minus 8 times 5 plus 12, all divided by this positive number. So we get 25 plus 12 is 37, and this is negative 40. So you're going to get negative 3 again over a positive number. So it's going to be still negative. And then if you put 7 in there, you can see that it's probably going to switch over to the x equals 7. You get 7 squared minus 8 times 7 plus 12 over a positive number. 49 plus 12 is 61. 61 minus 56 is plus 5. So you get plus 5 over a positive number. So this is positive. Okay. So you can see this is going from increasing to decreasing, which means a maximum. You also can say it's a maximum because it's concave down. So we're going to have a maximum here. And likewise, here you go from you're decreasing to increasing. That's a minimum. It's also concave up, which is also a minimum. So those all make sense. So the final thing we're going to do is we're going to evaluate the function at the critical numbers. So we're going to say, what is f of 2? So we go back to the original equation, which was x squared minus 6x plus 12, all divided by x minus 4. So that's 2 squared minus 6 times 2 plus 12 divided by 2 minus 4. So 4 plus, that's 16. 16 minus 12 is 4 divided by negative 2. And so we have negative 2. So when x equals 2, f of x equals negative 2. And then we do it at the other critical number, f of 6. So we get 6 squared minus 6 times 6 plus 12, all over 6 minus 4. So 36 plus 12 is 48, minus 36 is 12. 36 minus 36 is 0. So you get 12 divided by 2, which is 6. So this number is 6. Here it's undefined. At the vertical asymptote it's undefined. Okay, so we got a lot of stuff. We've got a few things left to do now. So we need the x-intercept. So that is when y is equal to 0. So we go back to our original expression. Y is equal to x squared minus 6x plus 12, all divided by x minus 4. So that's true when the numerator is 0. And is there a nice number way to factor that? I don't think so. Okay, so we take x minus 6x, that's equal to negative 12. And so you take half of that and you square it, you get 3 squared, negative 3 squared, which is positive 9. You add 9, you add 9, you get a negative number here, which means there are no x-intercepts. There are no values of x where the numerator goes to 0. So we can say no x-intercepts. Okay, then we have the y-intercept. That's when we set x equal to 0. So we go to the equation here and set x equal to 0. So we get y equals negative 3. 12 divided by negative 4 is negative 3. So that's a y-intercept. Okay, what else do we need to do? We need vertical asymptotes. So what we do is we look at the denominator. So that's the denominator is 0 when x minus 4 is 0. So we have a vertical asymptote at x equals 4. Now the horizontal asymptote, we don't have a horizontal asymptote. We have a slant asymptote. So what we're going to do is actually do the long division. So we'll take x squared minus 6x plus 12 here, and x minus 4 there. Okay, so what do we need to multiply x times by to get x squared? The answer is x. So you take x times x, it's x squared. X times negative 4 is negative 4x. We subtract that. So x squared minus x squared is 0. Negative 6x plus 4x is negative 2x. And then add 12, bring that down. And then we say, okay, what do we need to multiply x by to get negative 2x? Well, you multiply it by negative 2. So negative 2 times x is negative 2x. Negative 2 times negative 4 is positive 8. Again, we take the negative of that, and that goes, this drops out, so you have 12 minus 8, which is 4. So the original expression, which was x squared minus 6x plus 12 over x minus 4, becomes this term, x minus 2 plus 4 divided by the original denominator. So that is my same equation. So the slant part of it, the slant equation, is just the first two terms. This is the remainder. When x goes to infinity or negative infinity, this goes to 0. So the slant equation is y is equal to x minus 2, since when x goes to infinity or negative infinity, the last term, goes to 0. And that's what's left over. Okay, well, I think we have everything we need now. So let's add a page and put some graph paper on there. So let's go ahead and draw our slant line. And it's a straight line. Has a y-intercept of negative 2, slope of 1. So it's going to look something like this. And then it's going to go the opposite direction. So that's our slant asymptote. Okay, what else do we have? We have vertical asymptote at 4. So we'll draw that too. 1, 2, 3, 4. So we got vertical asymptote here. Let's see, we have a y-intercept at negative 3. So let's draw that in there. So negative 1, negative 2, negative 3. So that's my y-intercept. And then we have two extrema. Did we figure out what those were? Yeah, negative x equals negative 2, x equals 2, f of x equals negative 2. So we have 2, negative 2. So that's an extrema. And the other one was, I think 6. Let's go back here. 6, 6. X equals 6, y equals 6. So that's the other extrema. So we got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that's the other extrema. So again, this is the slant asymptote. We can't cross that, so we're going to just approach it, and then we go through that point, and then we have a local maximum right here, so we don't go any higher than that. It loops around and has to go back down this way. There are a couple of reasons why that's the case. So this goes down to negative infinity. Okay, now here, it has to stay within these boundaries. It can't come from here because you'd have an x-intercept. So we know it has to come from the other direction. It comes down. This is a minimum, so we know it can't go less than that. And then it comes over here and then approaches that. So if we go back to our table, which we will in just a second, we saw that from, let's go back and look at it here. So the table says for less than 4, we have concave down, and greater than 4, we have concave up. So let's see if that's true or not. So it's basically saying down up to this point, and then up after this point. And you can see that's true. This is pointing concave up, this is pointing concave down. Okay, what else do we know? The function's increasing, then it decreases, then it's decreasing, and then increasing. So it's increasing, decreasing, decreasing, increasing. So it's increasing until x equals 2, then it decreases. Across the vertical asymptote, it's still decreasing, and then it increases. So that also satisfies everything. So, you know, we have increasing, we have decreasing, we have decreasing, we have increasing. And what else? The second derivative is positive. Positive means that, which means we have a minimum there. The second derivative is negative here, so we know it's a concave down, which means a maximum. So all those things agree with what we said, and the final thing will be that we'll plot the function using the graphing program. So stand by if you're still watching. At this point, probably people are like, oh, calculus stuff is so long. It is. It takes persistence. So there it is. Let me take a picture of it. You can't see it yet, but it's just a piece of beauty. And let me add a page, drag that thing over. So there's the actual function. My slant asymptote is like this. So that's that line. My vertical asymptote is right here. My x-intercept, my y-intercept is here. You can see there are no x-intercepts. The red curve does not cross the x-axis. And there's my maximum. There's my minimum. These are critical points. This is also a critical point. So we said it's increasing up to this critical point, decreases down to this critical point, continues to decrease. And do we have any points of inflection? No, because it was concave down. Well, actually, we do have a point of inflection right there because then it changes from concave down to concave up. And that point of inflection is at the case where the second derivative is undefined, not equal to 0. Okay, check. Okay, the last two problems are going to just be polynomials. So those are a little bit easier. Pretty straightforward. So again, what we're doing is we are going to graph the function and label any intercepts, relative extreme of points of inflection, and asymptotes, and use a graphing utility. So let's go ahead and take the derivatives. So the first derivative is that, and the second derivative is that. So we need to find the critical numbers and the possible points of inflection. So we're going to look at each one of those separately. So we're going to set the first derivative equal to 0. And so we can factor out a 3x. So we get 3x times x minus 2, and that's equal to 0. So we get two values of x equals 0, and x equals 2. These are critical numbers. So these are possible places where you have a maximum or minimum. Then we look at the second derivative, so we set that equal to 0. And we'll get x is equal to 1. Divided by 6, we get x minus 1 is 0, or x equals 1. So these are possible points, possible point of inflection. And what we got before, for critical numbers, those are possible points where you have minimums and maximus. So we're going to make up our table now. Oh, do we have any vertical asymptotes? That's another thing to look at. Or are there cases where these are undefined? In the case of polynomials, we don't have anything like that. So really we just have, so we have two critical numbers. We have one possible point of inflection. I guess it's point of inflection. So how many in our domain, let's just talk about the domain. So because it's a polynomial, the domain goes from negative infinity to positive infinity. So our table is going to consist of three parts, which is the critical numbers and the possible points of inflection. We're going to have one additional interval. So we add these together and then add 1 to it. So that's 4. So we take 3, which is these two added together, plus the intervals, which is 4, plus one row for the headings. So it looks like we need a table that has 8 rows. And we have 5 columns because that's how it works out. So let's make our table now. So it's going to be 8 rows by 5 columns. 8 rows, 5 columns. So we'll just put it on one page, and I'm going to set it up like this. So we really don't have anything in this one. And then we have the values of the function. We have f prime of x. There we're looking for the sign, plus or minus. Here we're looking for a number. And f double prime is here. Where there again we're looking for plus or minus. And then we would have comments here. So here's where the intervals. The intervals in this case are vertical instead of horizontal. So we go from negative infinity to the smallest of the critical numbers or points of inflection. So what are these numbers? They're x equals 1 and x equals 0 and 2. So 0, 1, and 2. Let's write those down up here. 0, 1, 2. So those are how we're going to break the domain up. So we go to 0, and then we have x equals 0. Then we go from x equals 0 to x equals 1, x equals 1, x between 1 and 2, x equals 2, and 2 to positive infinity. So you see we cover the entire domain. In this case, we actually even include these in-between things. Okay, so those are the, that's how the table's filled out. So we can plug in, so let's put 2 pages up here so I can see this. So we can fill in the numbers now. So let's write out the function and all of the derivatives of the equation. So we have x cubed minus 3x squared plus 3, so that's the function. The first derivative is 3x squared minus 6x, and the second derivative is 6x minus 6. So what's going to happen is that the point of inflection is at this point. So the second derivative is 0 here, and the first derivative is 0 there and 0 there. So those are our critical numbers. That's our point of inflection. So all we have to do is actually to evaluate the second derivative anywhere between negative infinity and 1. So probably the easiest thing to do is to evaluate the second derivative here at 0. So we go put 0 into this equation, we get negative 6. So we put a negative sign there. And let's go ahead and put 2 in for the second derivative. So we'll have 2 times 6 minus 6 is positive 6. So that's positive. And because the second derivative only changes possibly across points of inflection, we can go ahead and fill out the rest of those. So it's going to be negative up until x equals 1, where it goes to 0 and then it becomes positive. Now for the first derivative, we just have to evaluate here, one of these points in here, and there. So again, we're looking just for the sign. So let's see, we're going to 0, so negative 1 probably is the easiest one to do it. So let me just, we're going to evaluate this at negative 1. And we'll evaluate this at 1 and evaluate this one at 3. So we're going to do the second derivatives of those values of x. So I'm going to do this in my head, but you can plug it in if you want to confirm it. But we'll have 3 times negative 1 squared, which will be 1. So that's positive 3. And then you have negative 6 times negative 1, which is positive 6. So this is positive, this is positive. Therefore, this has to be positive. Okay, at x equals 1, let's plug that in. So you'll get 3 minus 6 is negative 3, so that's negative at that value. And at x equals 3, you'll get 3 squared, which is 9. 9 times 3 is 27. That's 27. 3 times 6 is 18. 27 minus 18 is a positive number. Now we can go ahead and fill in the other ones because a function changes from increasing to decreasing only at critical numbers. So we know in this interval that it's going to be always negative, so we don't have to. Okay. And the last thing is we want to evaluate the function at these 3 values of x. So the first one's easy because these 2 terms go to 0, and so the value of the function is 3. If we plug in 1, we'll get 1 minus 3 plus 3, so those cancel out. So you just get 1. And then if you put 2 in, you'll get 8 minus, so this is 8. 2 squared is 4 minus 8 minus 12 is 4. Negative 4. So 8 minus 12 is negative 4. Plus 3 is positive 1, or negative 1. Negative 4 plus 3 is negative 1. And we don't worry about these parts right here. We're not going to put anything in there. Okay, so we have the function, all this table filled out. What we can say here is increasing. We can say decreasing here. This is so we're just looking at these values. This is decreasing, decreasing, and then it's increasing. That's based on those, the sign of those. And then we can do concave up or concave down. So I'm just going to write D or U. So that's concave down, and that's down, and that's down. And then we have a change here. So there's no change. Changes from down to up, 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 up. So there's comments about concavity. Okay, so now we go back and we do all the other things. So the next thing we do is the x-intercepts. So that's where y is equal to 0. So we take the function, so that equals 0. Now, this is where we can actually use some of the things we've already learned to help us figure out what maybe are x-intercepts. So let us, let's let's put a page in here for right now, and let's see what we know so far. So we have a point 0, 3. So x equals 0, y equals 3, so that's there. We have the point 1, 1, so that's right there. And we have the point -1, 2, -1, so 2, -1. So we have 3 points. And we see that we go from increasing to decreasing across here. So this is increasing. Then it goes to decreasing. It continues decreasing until we get to here. And then it goes to increasing again. Okay, so we're going to have 3 x-intercepts. One is going to be between 1 and 2, because this crosses, this is x equals 1 equals 2. So we know one intercept is around x equals 1.5 approximately. We don't know exactly for sure. It probably is exactly 1.5. Okay, so this is 2, this is 1, this is 0. So it looks like we might have one at around 3, and we might have one here. Looks symmetric, so maybe -1. So that's some possible. That's where they're going to be approximately. So now, when we actually pick values to try, in terms of when we factor this, if we want to factor it, we're probably going to pick x equals -1, x equals 3. I'm not going to choose that one because we'll get that when we factor it out. So if we get one of these whole numbers, hopefully one of these is a whole number, so then we can use synthetic division. So we have we have 1 x cubed, we have -3 x's, we have -3 x squared, 0x 3. So I'm going to pick -1 here. Let's see if that works. So we have -1, bring the 1 down. -1 times 1 is -1. And we get -4. -4 times -1 is 4. Bring that down. -4 times 4 is -4, and we get -1. So this has a remainder of -1. So this is not one of the zeros, but we do know that f of -1 is equal to -1. That's from what we learned earlier, so we don't completely waste that particular opportunity. And the next one is we'll pick x equals 3. So bring that down. 3 times 1 is 3. So you get 0. 3 times 0 is 0. Oh, sorry. Yeah, 3 times 0 is 0. You get 0. And 0 times 0 is 0, and so you get 3. Okay. So that actually says that f of 3 is equal to 3. And that's bothering me a little bit. So did I do something wrong here? I would have thought one of them was a 0. So I'm just going to look at this. Let's just go back to our graph and see if those make sense or not. So it says when x equals -1, then go to -1. And the other one was when x equals 3, we get +3. Now the question is, am I doing this? Did I do the wrong sign again? Let's try this. I always mess that up. I'll do the other way around. Okay, let's try it. 1 times, erase all that stuff. I'm pretty sure it's right. Maybe I'm just looking at it wrong. Maybe I should have tried -2. Anyway, let's just try this. Let's pause for a second. Sorry about that. Okay, well, I've just done a little thinking, and I've realized I did everything correct. Turns out the x-intercepts are not nice points. And if you look at the solution manual, they just show the x-intercepts. They don't explain how they got them. So how would you get them? Well, you'd actually have to, if you didn't have the graphing program, you'd have to kind of do it in a little iterative fashion. So let me just kind of explain how that works. You know, it turns out we can get pretty close with just what we have, the information that we have. So let's draw the graph, and then I'll come back if you're still interested. I'll explain how you would find the intercepts, even though they're not nice rational numbers. They are something else. So let's just plot what we know so far. We said that the value of the function at 0 was equal to, so we're going to go back to this table. Probably the best thing to do is to add a page in here, and I will bring the table up. And there we go. Okay. Yeah, I need to delete this page. I'm not sure why that was there. Okay, so there's the graph. So at x equals 0, y is equal to 3. Now that's also the y-intercept. If we set x equal to 0, you get, that's to find the y-intercept, you get x equals 3. Okay, then we had x equals 1, y equals 1, and x equals 2, y equals -1. And we said this was a max right there. So it comes down, and from our synthetic division here, trying to find some zeros, you can see -1 is another solution, or another point. So -1, 1, that's that one. And then we also did +3, which also gave us +3. So might as well use those. 1, 2, 3. 1, 2, 3. Okay, so it comes down like this, then it goes like that. Let's just check that. Also, that last point doesn't seem quite right. Let's make sure I did that right. 1, bring that down. 3 times 1 is 3. -3 plus 3 is 0. 3 times 0 is 0. Okay, well, that's what it says. I'm going to stop again. I'm going to look at the graph to make sure I'm not doing anything wrong. Okay, so that's correct. So then it comes down like that, goes through minimum, then it zooms up pretty quickly. It goes up like that. Okay. So if we were to look at this, let's just put on one page. It looks like my x-intercept is going to be between -1 and -2. So let me just write those off to the side. Between -1 and -2. And then it's going to be between +1 and +2. And then it's going to be between 2 and 3. So just based on this kind of rough graph, we've got 3 intervals. So what do we do now? So let's add a page. Well, you'd kind of create a table, and we're going to have x versus y, and let's make it about that big. And we just start picking values and then deciding what's going on. So, and also another thing we can do is that we know, so let's look at the first case. F of -1 is equal to +1, and F of -2 is, well, what's the function again? F of x is equal to x cubed minus 3x squared plus 3. So if we plug -2 in there, we'll get -2 cubed minus 3 times -2 squared plus 3. So that's -8 plus -2 squared is positive. Yep, okay. Make sure this, okay. So you get +4, so then you get -12 plus 3. So that's equal to -20 plus 3, which is -17. So it really goes down there fast. It's actually off the chart. So it's way down here. So it's really steep. So it's going to be closer to -1 than it is to -2. So this is x, and this is f of x. So you can actually interpolate, if you think about it. This is +1, this is -17. So the value of x that I'm going to pick, my first guess, is going to be equal to -1 plus the ratio of the distance from here to, let's see here, so it's going to be 1 y unit divided by 18 units, because I'm going from +1 to -17, so that's 18 units. And then we're moving -1 in the x direction. So if you do that, you'll get -1 point. So let's try what it is here. -1 minus 1 divided by 18. So I get -1.055. So then you plug that into the equation. So what we want to do is find f of -1.055. And then when you'd work it is you'd set up your calculator to have enough space that you could change these numbers maybe to the third decimal point. -1.055, quantity cubed, minus 3 times the quantity, -1.055 squared, plus 3, and I push enter, and I get, so a -1.055, I get f of x is -1.51. So then -17. Okay, but it's still negative, and I started from -1, +1, so I can do the same kind of thing. Let me add a page. So my next guess is I'm going to use these two endpoints. I'm going to take x is -1.01, -1.0, y was +1, and then I'll take this new point, -1.055. That gives me -1.51. Okay, so again, I'm going to interpolate to try to find where this goes to 0. So in this case, what I would do is I take -1 plus, and I'm going to take the ratio of 1, which is the distance from 1 to 0, and divide by the total difference here, which is 2.51, and then multiply by this difference, which is going to be -0.055. So -1.0 plus 1 times -0.055 divided by 2.51, and I get, my new guess is -1.022. Okay, -1.022, and I go back to my equation that I've saved, and I just change the numbers so I don't have to rewrite the equation, and I push enter, and I get I should be getting closer than this. I'm doing something wrong. See, I got that. And I would expect my next guess to be much closer. So let me just try something here. Oh, that should be -1. So that actually means that the intersection is on the other side. Did I really do that? Oh, yeah, -1. So that was where I messed up. So I should have at x equals -1, y should have been -1. Okay, so that's where I made a mistake. Okay, so let's try it over. So it's going to be between 0 and 1. So I'm going to erase all this stuff here. So what this proves is, and you probably figured this out already, everybody makes mistakes. The question is, how do you respond to those mistakes, or how do you figure out if you get messed up? So we're going to go back here. X equals 0, y is equal to 3, and at x equals -1, y was equal to -1. Okay, that's going to work better now. So my first guess is going to be 0 plus my change. I have 0 in here, so to get from 3 to 0 is 3 units. To get from all the way across is 4 units. And then I multiply by this difference, -1. So you can see I'm going to use x is equal to -3/4. Okay, now I'll put that in my, so -0.75 and -0.75. Okay, so at x -0.75, f of x is 0.89. So we're still above. So now what we do is we would, again, what we're going to do is we're going to use this as the left-hand side, -0.75, y is equal to 0.89. Then we'll use the other side, -1, y equals -1. And so my new guess is going to be -0.75 plus 0.89 divided by 1.89 times the distance, the x distance, which is 0.25, -0.75 plus 0.89 divided by 1.89 times 0.25. I get x is, something's wrong there. Oh, that's negative. Was that where I messed up before? No, I did that right. Okay, let me just fix this. So it's negative minus, okay. So I get -0.8677. -0.8677. Okay, now we plug that back into the function. -0.868. Basically, I'm just doing it 3 decimal points. And we go 868. And I get y is equal to 0.086. So you see I'm getting pretty close. So let's do it one more time. So x is equal to, we're still above, we're still greater than 0, so we can say x is -0.8 677. The y value is 0.086. Then we do the second one, x is -1, y is equal to -1. We do the same calculation. So we start at 0.8677 plus difference between this and 0 divided by the total difference, and so that's 1.086, and we multiply by negative this difference. So we take 1 minus 0.8677, and we put in parentheses where we're supposed to. Okay, so it's 0.132. Okay. So negative 0.8677 plus 0.086 divided by 1.086 times negative 0.132, and that'll give me negative 0.878. Negative 0.878, and then we use that in our equation again for the function, and I get 0.0. So you can see we're getting pretty darn close now as far as the value. So the x-intercept is that. In the book they say negative 0.879. So if we do one more iteration, we get 0.879. That's the correct one. Okay, so you could do the same thing for the others. Same kind of arrangement. Okay, well, you stuck with me for that long. Congratulations. Okay, this is our last problem. It's another polynomial. If you watch the last video, one thing you might have noticed is it's very difficult to get a case where you have the critical numbers, the points of inflection, and the zeros to be all nice whole numbers. So usually one of them is messed up. In the last problem, we got nice numbers for the critical numbers and the point of inflection, but we did not get good numbers for the zeros. And I think it looks like that might be the case here, especially since we have 5/3 at the end of this thing. So we may just forget about the zeros right now. And actually, I'm going to just take a quick peek at the solution. And I don't see any comment about zeros. So we're not going to worry about those. We can at least know what values of x they're between. Okay, so the derivative is 12x cubed minus 12x. And the second derivative is equal to 36x squared minus 12. Make sure I did that right. Looks good. Okay. So let's go ahead and find the critical numbers. So that's where the first derivative is equal to 0. So we set that equal to 0. And we factor out a 12x. And that leaves us with x squared minus 1. And so we've got x. I don't know why I put that in parentheses. 12x times x plus 1 times x minus 1. So we have three critical numbers. X equals 0, x equals 1, x equals negative 1. Actually, that comes from there, that comes from there. So those are our critical numbers. So those are possible values of x where we have minimums or maximums. possible values of x where the function changes from increasing to decreasing. But it doesn't guarantee it. And let's go ahead and do the second derivative part over here. So the possible points of inflection. And again, those occur when the second derivative equals 0 or the second derivative does not exist, which in this case, it always exists. So we're just going to look at the case where it equals 0. So you get 36x squared minus 12 is equal to 0. If we divide by 36, we'll get 1/3. 12 divided by 3 is 12 divided by 36 is same as 1/3. So you get x squared is equal to 1/3. Take the square root. So x is equal to plus or minus the square root of 1/3, which is the same as the plus or minus 1 over the square root of 3. And if we multiply the numerator and the denominator by the square root of 3, we get the square root of 3/3. That should look familiar if that's the tangent of pi over 6 or 30 degrees. Okay, so, and that's plus or minus. Let's drop the plus or minus. So those are my possible points of inflection. So we're going to make a table. It's going to have a lot of elements in it. It's going to have 2 possible points of inflection, 3 critical numbers, so that's 5. Then you're going to have 6 intervals, 1 more than those, so you have 11, plus 12, 1 more for the heading, so it'll be 12 rows by 5 columns. So that's going to be our table. So 5, we're going to actually make it 6, and then we're going to double it to make it so that it, so what we'll do is we'll, oh, what happened there? Click there, we'll clone it, and we'll move that out of the way. And then we will take it to the top, make it bigger. Maybe I should have cloned it now, but it doesn't matter. It's not that big a deal. Okay, so we line those up so that it makes one big table. And then we drag this down so that it's the same width, and now the whole table should fit together quite nicely. Okay, so there's your table. And that doesn't have anything in it. Then we have f of x. We have f prime of x. We have f double prime of x. We have the comment. Okay, so let's put this on one page, and we're going to write. Before we do that, let's select all, and then we're going to move this thing down. Like that, and then we'll write in all those numbers. So we've got -1, negative the square root of 3/3, 0, positive the square root of 3/3, and +1. Those are all the 5 numbers. So now we're going to put it on one page so we can write these in a little easier. So we do the whole domain in pieces. So we go from -infinity to 1, then we include 1, then we go from -1 to negative the square root of 3/3, then we go for x equals negative the square root of 3/3. Then we go from negative the square root of 3/3 to 0. Then we do x equals 0. Then we go from 0 to positive the square root of 3/3. X equals the square root of 3/3. From the square root of 3/3 to x equals 1, x equals 1, and then from x equals 1 to infinity. So we go from x equals 1 to positive infinity. So those are all of our things that we're going to consider. Okay, now we'll go back to 2 pages so we can see all that stuff. And let's write down over here everything we need to know. I'm going to add a page so we can get it all in one little spot. So the original function, f of x, was equal to 3x to the 4th minus 6x squared plus 5/3. F prime of x was 12x cubed minus 12x. F double prime of x is equal to 36x squared minus 12. So those are the functions. And I'm going to write in small letters, small numbers, what we're going to use for the test points. So I'm going to use -2 here. What is the square root of 3 over 3? So the square root of 3 divided by 3 is 0.57. So I can use, say, -0.7. Here I'll use -0.2, and then I can just do the same thing on the other side. So +0.2, +0.7, and +2. So those can be my test values at each one of those. Okay, now let's put a little comment about what these are. So these -1 was critical number, and 0 was a critical number, and +1 was a critical number. Okay, and this is the possible point of inflection and the possible point of inflection. So why I'm doing that is that, you know, the second derivative was equal to 0 here, and it was equal to 0 there, and the first derivative was 0 there, and 0 there, and 0 there. So what we're going to have is these things changing signs possibly. So I only have to evaluate the second derivative at one of these values. And actually it might be the easiest is to use -1 here to calculate the second derivative. So I'm going to use -1 here, and I have to use 0 there, and then +1 for the other stuff. And then here I can use to evaluate the first derivative. I don't have to worry about it because I just have to do it at one point in there. So, okay, so what am I going to do? I think I'm going to use -1 here for the second derivative. So let's look over here. -1 squared would be +1. 36 minus 12 is a positive number. So this is going to be positive at this point. Let me use green. So this is positive. I just plugged -1 in there. I got positive. So this is positive, and this is positive. Okay, if you plug 0 in, you'll get -12. So this is negative. Therefore, this has to be negative, and this has to be negative. And then I plug +1 in, and I'll get 36 minus 12, which is positive. As a consequence, I can make those other ones positive as well. Okay, so I've got that filled out. Now, here I only have to do 4 values. And so I'm going to pick -2. So -2 cubed is negative. Negative times positive is negative, so that's negative. And this is going to be positive. So -2 cubed is -8. -8 times 12 minus 1 time, or -2 times 12, -12. Anyway, this is going to be more negative than that, or this is going to be more negative than that's positive. So I know that's going to be negative right there. Okay, now here I'll put in -0.2. So -0.2. So what's going to happen is, what you can see is that anytime you have a fraction, so let's say 0.2 cubed is always going to be less than 0.2 in this case. And they're both multiplied by 12. So when the number here is between, well, from negative, okay, so it's going to be negative. So this is going to be a smaller negative number than this is going to be positive. So this is smaller negative, and that product is going to be, magnitude-wise, is going to be smaller than that. And this is going to be a negative number because 12 times negative 0.2 is positive, pardon me, 12 times negative 0.2 is negative. Negative times negative is positive, so this is going to be positive, which is going to be bigger than that. So it's going to be positive at this value. So I can put positive in there. And if I use positive 0.2 instead, same kind of deal. This number is going to be positive. And so I'll end up with positive times a positive, and then I'll have a positive times a negative, which is a positive times a positive, which is negative. So then I'll have this whole thing will be negative. And this term will be bigger than that term. So it'll be negative. You can just plug the number in if you want to. I'm just doing this, trying to do an order of magnitude. Likewise, put positive 2 in there, you'll get 8 times 12 minus 2 times 12. So obviously this is going to be bigger, and this is positive, and this is negative. So that's going to be positive. And it makes sense because it's changing across. Polynomials do that kind of thing. They change across the critical number. And then we can plug the numbers into the original expression. So let's do that. So f of negative 1. So I'm going to write this, do it in my calculator so that I can change this value. Actually, what I'm going to do is I'm going to do it at this point, and then I can always, that's the most complicated one. So negative the square root of 3 divided by 3 raised to the 4th power. 3 times negative the square root of 3 raised to the 4th power minus 6 times negative square root of 3 divided by 3. That whole thing squared plus 5 divided by 3. 3 times 2. I get 0. Does that make sense? I don't know. Makes sense. Okay. So we do that all right. Okay, let's just do the other values. So now I'm going to do positive square root of 3 over 3. And I think I can put a positive in there. It might not like that. No, it doesn't like that. Okay, so I'm just going to delete the sign. So delete and delete. I get 0 again. Okay. So that's the y value. Okay, now let's do it again. We're going to put in negative 1. Negative 1. Delete, delete, delete. Negative 1. Delete, delete, delete. Okay, push enter. And here I get negative 1.333. When x equals 0, I get 1.666. That's 5/3. And oh, I should have been here. 1.666. And now I stick in positive 1. I think so delete the negative sign. I get negative 1.33 again. So you see this is kind of symmetry. Okay, so that's all we have. And the last thing we can do is we can make some comments about whether the function's increasing or decreasing. So it's decreasing, increasing, 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 decreasing, 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 increasing. Okay, so that's from looking at the sign. And then if you look at the second derivative, it's concave up, 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 down, 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 up, up, up. Okay. So what we'll do is we'll use that information to graph what's going on here. And what I'm actually going to do is we're going to make this so that it's every third value is 1 unit. And we're doing that because a lot of the stuff's breaking up into thirds, so I think it might just be easier to plot it in that case. So this is 1, 2, 3, -1, -2, -3, 1, 2, 3, -1, -2, -3. Okay, so let's plot there we have 5 points here. So we have -1, -1.33, which would be that point right there. We have negative square root of 3 over 3, which is 0.577, I think. So that would be about right there. And 0, so you get that point. At x equals 0, we're at 1.66. At positive, the square root of 3 over 3, we are at 0. And at x equals 1, we're at negative 1.33. Okay, so those are the 3 points. And we know this is a minimum. Why do we know this is a minimum? Because it's concave up. So we know that's concave up. We know this one's concave down because the second derivative is negative. And then we have concave up. Okay, so it's going to be curving like this. It's going to go up through this point, which actually is the x-intercept. So it turned out that it wasn't that bad. We'll actually figure that out in just a second. Now that we know it's easy to do, we'll see how that happened. And then like that. Okay. So now the question is, it's going to go up. So this is going to continue to go up. And just by symmetry, it looks like the x-intercepts, we've got two other x-intercepts, which we can calculate here in a second. So that goes up. And this is a fourth order equation. It's an even function, so it's going to look something like that. So is this all true? It's concave up until this point, then it's concave down, then it's concave up. So we're seeing up, down, up. The function is decreasing until you get to x equals -1, then it's increasing until you get to x equals 0, then it's decreasing until you get to x equals +1, and then it's increasing. So everything works out. Everything makes sense. The only thing we don't have is the zeros, so let's go ahead and do that. So so we're actually going to use this information to calculate the other two zeros. So we know that f of the square root of 3 over 3 is equal to 0. And we know that f of negative the square root of 3 over 3 is equal to 0. So if we took these factors, x plus the square root of 3 over 3 and x minus the square root of 3 over 3, and we multiply those together, we'll get x squared minus 3 over 9. 3 times 3 is square root of 3 times the square root of 3 is 3. 3 times 3 is 9. Okay. And then we've got something else, and when you multiply those together, we get the original function, except there's going to be some factor of 3, so I'll put a 3 in there. So 3x to the 4th minus 6x squared plus 5/3. So we're going to have x squared, and it's probably going to be minus something. So how do we figure that out? What is that? Well, what we can do is use well, actually what we can do is we can rewrite this as 3 times x to the 4th minus 2 plus 5 ninths. So I'm factoring out of 3. So you divide this by 3, divide that by 3, and divide that by 3, and you get that. Okay. So that's the original expression. And because this is squared, we can't, well, we could use synthetic division. You'd have to realize that, so let's use this as synthetic division. What we would do is we'd kind of break this down into really a quadratic form. So let's just do that. So what we'd have is 1 minus 2 and then 5 ninths up there. And what we're going to divide by is okay, what is it? Is it going to be 3 ninths or 1/3? That's 1/3. Let's go ahead and fix that. 1/3. So yeah, I think it's going to be negative 1/3. So that's negative 1/3. So so we're going to put 1/3 right there. If you don't completely understand this, don't worry. But otherwise, we'd have to use long division, which is still fine. So let's see if this works. So you bring 1 down. 1 times 1/3 is 1/3. Okay, add these two together, and you get negative 5/3. Negative 5/3 times 1/3 is negative 5 ninths. You add them together, you get 0. And so this term is going to be equal to, you're going to have x squared minus 5/3. So this is going to be 5/3. Okay. So now we can solve this part. So we're going to set that equal to 0. That's going to give us the other two zeros. So you get basically x is equal to plus or minus the square root of 5/3, which is square root of 1.66. I'm just going to do it as a decimal because we're going to look at it on the graph. So the square root of 5 divided by 3 is 1.29. So we're going to have plus or minus 1.291. So that's going to be the other two x-intercepts. And so the best thing to do is to plot the whole thing and then prove that it's all work. We're going to check the x-intercepts first and all the other stuff. So I'm going to stop sharing this, start sharing, get the graph, graphing programs. There it is. And the function we're looking at is 3x to the 4th minus 6x squared plus 5 divided by 3. So we graph it. There you go. It looks just like we thought it would look like. And we're going to zoom in a little bit so we can see this in more detail. Wrong way. Okay, so there we go. So if we take our cursor and we put it right there, we get negative 0.58, which is equal to the square root of 3 over 3. And here we have positive square root of 3 over 3. We get a maximum at 0, and we get a maximum at x equals negative 1. Minimum at x equals negative. Positive 1, x equals negative 1. Okay, here is the thing we just figured out. There's the x-intercept, negative 1.291. The other x-intercept is positive 1.291. And therefore, everything works out. So now I'm going to take this and just bring it in to the solution. So let me grab that. And let's see here. Go back to that. Okay, so there's the actual result. But before we do that, let's actually just add a page and plot all this stuff. Well, we already did that. So there you go. And what we found out was that this is 1.29. Remember, let's go back here to remind ourselves that we got 1.291. And then that was the graph. So these were our critical numbers. We had 3 critical numbers. Our point of inflection was at, where was our point of inflection? Oh, it was actually right in the middle here. So it was there. That's also where our zeros were. So we got those 2 zeros, 2 points of inflection. Then we were able to get these other two zeros. So they're 4 across the x-axis 4 times. Our y-intercept, we never did calculate that, but we could do it. Well, it's 5/3. We did do that. So this is 5/3. This is minus the square root of 3 over 3. This is plus the square root of 3 over 3. This value was the square root of negative the square root of 5/3. This was positive the square root of 5/3. This was 0. This was -1. This was +1. So that's all there is to that thing. So yes, my head is spinning as well. And I think that's all that I have to say about that. Just want to check something here. Make sure everything makes sense. Yep, okay, we're good.